Okay, I think it's time to look at an example. Let's start with the function f of x equals the natural log of the quantity 1 plus x. And we want to find the first Taylor polynomial for f of x based at b equals 0. Well, the Taylor polynomial in this case is just the linear approximation, and we know that that's going to be f of b plus f prime of b times x minus b. And we know that b is 0, so we can substitute 0 in there. Get f of 0 plus f prime of 0 times x minus 0. Well, if f of x is the natural log of 1 plus x, then f prime of x is equal to 1 over 1 plus x. If you evaluate these at x equals 0, you're going to get the natural log of 1, which is 0, or f of x at 0. And here you're just going to get 1. So I can replace those. F of 0 is the natural log of 1, or 0, right? I said 0. So 0 plus f prime of 0 is 1 times x minus 0 is x. So I have 0 plus 1 times x, which is just x. So my linear approximation for the function f of x equals the natural log of the quantity 1 plus x is the line y equals x. Let's start by checking that that actually makes sense. Let's graph the function f of x. Now this is the function, the natural log of x shifted to the left 1 unit. I could write this as x plus 1 instead. And so that, since the argument is 1 larger than x, it shifts the graph to the left 1. So instead of having a vertical asymptote at 0, I have a vertical asymptote there. And I have something that looks something kind of like that. And then my tangent line is the line y equals x, which looks something like that. And this line, these two lines, or these two curves rather, are tangent at the point x equals 0, and their slopes are the same there, and their values are the same there. At exactly x equals 0, x equals 0. And the natural log of 1 plus 0 is the natural log of 1, which is also 0. But either side of that, there's some small error, a little bit here, a little bit more farther out, and quite a bit more farther out. And it's the same in both directions. In fact, the error gets very large very quickly on the left-hand side. It doesn't go quite so quickly on the right-hand side. But we can still use y equals x. If I could zoom in here, I can't do that with this software, but if I could zoom in here, I could use, I could estimate values of natural log of 1 plus x for values very near x equals 0, and get pretty good approximations just by plugging those values into the function for the line. So this linear approximation, this first Taylor polynomial, makes sense for this curve, for this function here, near 0. Another question that it makes sense to ask here is how big is the error once I move away from 0 a certain amount? How big is that error? Another question is, how big do I want the error to be, and what is the interval in which I can work in order to guarantee that error is no bigger than that? This isn't a good example to use for that because the error gets big so fast in both directions that it really doesn't make sense to address those questions here, but I will be addressing them on the next 2 slides. I have 2 more examples to do. They're related to each other, but I will be addressing both finding the tangent line, finding the first Taylor polynomial, and finding the error bound and finding the size of an interval to restrict the error bound. Okay, this is example 1.1 in your course pack. We are asked to find a bound for the error in approximating a function using a Taylor polynomial. In other words, find the largest error that will occur if we use a Taylor polynomial to approximate this function on this interval. So the first thing we need to do is figure out what that Taylor polynomial is. It's not actually, strictly speaking, necessary that that's the first thing we do, but it certainly makes sense that it's something we're going to need to do. And so we might as well do it now as later. We're also going to need, eventually, f prime of x so that we can evaluate it for our Taylor polynomial, and also f double prime of x so that we can find our m value. So the derivative of tangent inverse is 1 plus 1 over x squared. And the derivative of that, the second derivative of tan inverse, is negative 2x over 1 plus x squared quantity squared. So I have my first and second derivatives of f. And what I'm going to do now is I'm going to start by finding the first Taylor polynomial. And I know that to be f of b plus f prime of b times x minus b. I also know b to be 1. It's given to me, right? I know I've been told to center my work at x equals 1. So I have f of 1 plus f prime of 1 times x minus 1. And I also know, or I can find out, what f prime is, what f is, and what f prime is at 1. Let's just go ahead and do f of 1 first. The tangent inverse of 1 is the angle whose tangent is 1, and that's pi over 4. And if I evaluate f prime at 1, I put a 1 in here, I get 1 over 2, so I get a half. So I have 1 half times x minus 1. That is my tangent line approximation. There are different ways you could write it. You know, I could distribute my 1 half and then combine my constants, and I'd get a true sort of y equals mx plus b expression, but it's not, strictly speaking, necessary. This is the tangent line approximation, or the tangent approximation for f of x equals tan inverse of x near 1. All right. Now, the question we were asked here really is, what is how big is the error likely to be, or what's the biggest possible error on this interval? So what I'm going to do is set out my formula. E, there's an m in it. E is less than or equal to m over 2 times x minus b, and that's 1 in this case, squared. And then I need to go back and figure out what m is. Well, m is the largest possible value that f double prime can be. So I want to take a look at this thing right here and see how big can this get? And by big, I mean, what is its magnitude? When I introduced m, I said it was the biggest value the second derivative could be. And by that, I don't mean the highest possible positive y value on a graph, but just simply the largest magnitude. So what we're really interested in here is letting m, sorry, that's the wrong color. We want m to equal the absolute value of the second derivative. And in this case, that's going to be positive 2x over 1 plus x squared quantity squared. That positive is important because we are looking not at is the value that we're looking for above the x-axis or below the x-axis. We're not interested in whether it's positive or negative. We're interested in its size, in its magnitude. So we're going to be using not the actual second derivative that we found here, but this positive version of it. Now, if you want to find out what the largest possible value of this function is, there are several ways that you could go about doing it. One is that you could graph it and just look at the graph, and in the case of Desmos, you can actually click on what appears to be the largest value on the graph, and Desmos will tell you an approximate value for what that y value is. So if you graph this function on Desmos, for example, you can find out what the largest value of the function is in Desmos. Or you can take its derivative and set that equal to 0, and that'll tell you where this function has extreme values. If you look at a graph of this function, it's a bit of a weird looking function. It's pretty cool, actually. Unfortunately, we're not interested in the cool part. We're only interested in the piece of the function between x equals 0.9 and x equals 1.1. And over that very short interval, just looking at the graph of the function, I can see that x equals 0.9 is the highest point. If I took the derivative of this function, I'd very quickly be able to tell that the function is decreasing across its entire interval. In other words, its derivative is always negative. So its slope is always negative, and that means the function is decreasing, at least over that interval. Now, what I'm interested in is the largest possible value this function can have. So I'm going to take the value of, this isn't f of x, but f double prime of x, take the value of f double prime of x that occurs at x equals 0.9, and that's about 0.55. It's 0.5494. So if I let m then equal 0.55, that will give me the value for m that guarantees that this function, this expression here, is larger than e. In other words, e will be something less than that value. So I'm going to let m equal 0.55, and that gives me that e is less than or equal to 0.55 over 2 times x minus 1 squared. Now, since I want to know where my error is less than this right-hand side, I want to find out where the right-hand side is as big as possible. So I'm going to, again, take a look at a graph of this thing or find some other way to find its maximum values. Graphing this function on Desmos gives me something that kind of looks like this. Around x equals 1, a very shallow parabola. And between 0.9 and 1.1, I have, you really can't even see it here. And this is exaggerated, this is not accurate. The point here is 0.9 comma 0.0027. And the point here is 1.1, 0.0028. And because what I'm trying to do is guarantee that this error is smaller than whatever I come up with over here, I want to use the largest possible value I can get for this thing so that I'm guaranteed that this error will be smaller than that. If I use 0.0027 for my right-hand side here, then there is a situation in which the error could be bigger than that, and that is on this other side of the interval here at 1.1. The error there is actually larger than 0.0027. So I'm going to use the value 1.1 because it returns the error 0.0028 instead of 27. So remembering now what it was we were looking for, we were actually asked in this case to find the error bound, and that error bound is 0.0028. What that means is that as long as I'm working in this interval right here, this small interval right here, I can use this function instead of arctangent to approximate values of arctangent within an error bound, within a boundary of 0.0028. I won't have any errors bigger than 0.0028. As long as I stay within this boundary, within this interval, I can use this function to make those estimations. It's also important for me to point out that what we're doing here is finding error bounds on tangent lines, on T1. We're not finding error bounds in general for Taylor polynomials here, just for first-degree Taylor polynomials. So just for linear approximations. All right, now we're going to do another example, but it's actually really the same example, but we're going to be looking at it from a different angle. In the next example, I want to take a look at this same function. I will use the same linear approximation, and I'm going to be asking the question, what is the interval so that my error will be no bigger than 0.001? In this problem, I gave you the interval, and I asked you to find the error bound. In the next problem, I'm going to give you the error bound and ask you what the interval is that will guarantee that that error is no bigger than the value I give you. Okay, so for the same function, for the same center value, and for the same interval, well, not for the same interval, in fact, let's cross that out. We want to find the interval over which the error is at most 0.001. We know, or we have a formula, if you will, for error. It's m over 2 x minus 1 quantity squared. And in this case, we want that to be that error, that formula, that value, to be equal to 0.001 so that the error is less than that. The error is less than this side here. Well, that's pretty easy to solve for. We just need to solve for x here, right? What we're doing, though, is be careful, is we're solving this equation, and then we're going to use it to answer the question about this value here outside that equation. So let's do the algebra here. Let's see if I double that. Well, first of all, we know that m is 0.55 from our previous work. And now I'm just going to solve this for x. So let's see if I'll write this as x minus 1 squared equals 0.001 times the reciprocal of my fraction. And then I'll take the square root of both sides. Let's do that much first. I have 0.001 times 2 divided by 0.55. That gives me about 0.0036. And then I'm going to take the square root of that. And that gives me x minus 1 is equal to 0.0603, roughly. And then I could add 1 to both sides. X equals 1.0603. But notice I just kind of threw the absolute value bars on this. There's two reasons for that. One is that this x minus 1 quantity was squared. It's squared in this formula in the first place. So when I take the square root of it, I know that that's going to be a positive number. The other thing is that what I'm looking at here is what is my distance from B? What is the distance from B, right? Because my interval here, my distance from B, the interval that I was given in the previous example was 1/10 either side of 1. And I want to know what my distance is either side of 1 in order to guarantee an error of smaller than 0.001. So I want to know, I don't really want to know what x is as much as I want to know is how far away can I be from this number 1 either side of it. So I threw these absolute value bars on here to kind of help me remember that this is a distance that I'm working with. So I've solved for x here, but that's not really what I want. What I want is the interval 1 minus 0.06303 to 1 plus 0.0603. And if I do the arithmetic here, I get 0.9397 to 1.0603. So that's the interval size I need, or the interval that I need, if I want to guarantee that my error is inside 0.001, smaller than 0.001, or at least no bigger than that value. I would strongly encourage you to read the word of caution at the bottom of page 6 in your course pack. It's an interesting note that the work that we've been doing here is foundational and fundamental and interesting and valuable, but we can't always tell what the interval might be that we should be working with. It's not always quite as straightforward as it has been in this example. The other thing I want to encourage you to do, if you haven't already done it, is to go back to the course pack, to the beginning of this section, and read through the scenario about Ken and his son, and read through the setup of that problem. I'm not crazy about starting this course with that as an example, as a motivator, but now that we've been through some of the math, I think it's quite an interesting way to see how this concept can be useful. It also shows, kind of illustrates how the error bound can be used, and how you can come up with an error, a value for the error, and an interval for the error based on the information in that scenario. So I think it's a valuable read. I just didn't like to start the section with it because I don't know. It's my personal preference is that it's not particularly motivating. So that's it for this section. After this, you'll find on the next page in Canvas, you'll find a homework assignment. It consists of 7 problems. The first several are just calculus review, and the rest ask you to review and practice what we've learned in this section. So enjoy that exercise and be prepared to turn that in. You'll be submitting it as a PDF. You can either do your homework on separate paper, actual paper, and then scan it and upload it, or you can do it as on digital paper. You know, if you use OneNote, for example, or some other software for writing on your tablet, you can do your work on screen and upload the digital version. That's absolutely fine. I'll be looking for a PDF. And then once that's been submitted, I'll be looking at those and returning any feedback I have for you, and then we'll be ready to go on to the next section. Sections 2 and 3 in your course pack cover quadratic approximations and higher order approximations, and it's only after section 3 that you'll see your second homework assignment. So that's it for now, and I'll see you in the next video.